In the earlier video we had stopped at this point. Now we will take the story forward. This we see is a metal from which electrons got ejected when a light of a suitably small wavelength was incident on it. Now we know that there is something called a dispersion of light. There's a when light is passed through a prism at a, I don't remember what angle it was. At that angle, when it passes out of the prism, on the other side 7 colors disperse. That is, white light is made up of all the colors. But as we say that if we say that here there is a light source, and light source photons come from the light source of a suitably small wavelength, we only mean that there is only one wavelength. That means that there is only, the light is of some color, of one particular color, but not white light, which is made up of all the wavelengths. If I think I'm clear. This is not only a light source, it is a monochromatic, single color, monochromatic light source. That's the only thing which I want to make clear about this picture before we start. So now there's no electrons on the surface. They are very close to the surface, and they are a bit away from the surface. If this is the surface, these are the electrons. I'm going to write the electrons. Actually there are atoms, but it's only concerned with the electrons, and there may be some which are a bit away. Too big for electron. Just a minute. There is a surface and there are electrons, some close to the surface, some a bit far away from the surface. Now when a monochromatic light is incident, say on this electron, this which is very close to the surface, on this electron got lost, this electron will eject without any problem, because it is so close to the surface, that is, it cannot collide with anything else, so it will simply eject. But we cannot say similarly about the electron which is a bit away from the surface. Let's say there's an electron here, and light somehow reaches that electron. That electron cannot simply get out. It has to collide with so many other electrons, atoms, and that it cannot simply get out of here. So even if a suitable energy is incident here on this electron, it will not get out as easily as this one. It may lose all its energy in only the collisions. Now we see this is a point which I was supposed to say as the second point. The first point is a metal is a vast attraction. A metal is attraction. It is huge store of so many atoms, and there is attraction between the atoms and the molecules. Therefore the metal holds. Therefore the metal exists. Now when there is an incident light and it falls on an electron, it tries to escape, but it cannot escape because of the attractive force inside the metal. So it will get attracted back, it will get pulled back into the metal. So it only implies that there has to be a certain minimum energy which will be equal to the attraction energy, so that it gets cancelled, so that the attraction energy gets cancelled by that minimum energy which will be provided by the incident light. So that minimum energy which we hope gets cancelled by the incident light is called phi. This symbol is called phi, and it's called work function. It's called work function only here It's called, this symbol is called phi, appears differently in different subjects and chapters. Work function. So work function is the first thing which I should have said, that the work function, the minimum energy which must be fulfilled by the incident light so that the electron escapes, is the work function. So if this electron, which is the closest, light falls here, this electron is the closest, so if I give it the work function, it will cancel and this electron will just come out with zero energy. You get what I mean? It is the closest to the surface. There is no chance of collision. That electron will get a work function. It will get a work function of energy. That is, if there is 2 is the work function, it will get 2 incident energy from the photon. That photon's energy will be 2. Let's say 2 joules. Okay, that's too much, that's a big quantity, but let's say 2 joules. So it will only it will cancel the pull, and the 2 joules will get consumed in fulfilling the work function, and this electron will get ejected, but it will get ejected with zero speed. And because it will get ejected with zero speed, it will have zero kinetic energy, because kinetic energy is, oh my god, kinetic energy is half m velocity squared. It will be 0 because the v is 0 here, the velocity is 0 here, so it will come up with 0 kinetic energy and 0 speed. If there is a movement of electrons, obviously kinetic energy comes into picture. It's all dealing with energies here. There's a work function, there's the energy of the photon, there's an attraction energy of the metal itself, the work function. Now this is the normal terminologies attached to this little concept. And now we see the first point was the work function 1. The second point was that the electrons at the back side, which are a bit away from the surface, have to collide with a lot of other particles, so they lose their energy. The ones closer to the surface do not lose their energy because there is no chance of collision. So basically the particles at the surface have the highest kinetic energy, they have the maximum kinetic energy, and those beyond have a very have reduced kinetic energy or zero kinetic energy. It may happen that there's a work function of only 2, they get an incident 2 joules, they get an incident energy of 5 joules. That's too high quantity for all this, but let's say that they do get it. And it may happen that all this energy gets wasted in only the collisions, and it may never come out however greater the incident is. But it does come out generally, but if it may get all wasted in the collisions itself. So this is the kind of third point, that it may never come out because it may get wasted in the collision. So to get the maximum kinetic energy which we can have from an incident light, is the K is the maximum kinetic energy. K is the kinetic energy. The maximum kinetic energy which we can have is E minus phi. Phi is a work function. This is E, we have seen before, h nu and hc by lambda, h nu minus phi, or hc by lambda minus phi. Now this phi has to be, for ease of calculations and all purposes, this has to be expressed in a similar method. So obviously it's very obvious that if there is a threshold energy level, there's a work function. There's also something like threshold wavelength and threshold frequency. I think it's here, maybe. No. Let's say it's here. I had forgotten where it is. I think it's here itself. It's located. So again we write that K max equals to h nu minus h nu naught. The nu naught is the threshold frequency of the metal. The threshold frequency of the metal, and higher the frequency, greater the kinetic energy with which it releases from the metal. So it is h nu minus nu naught. And for the wavelength part, it is hc by lambda minus hc by lambda naught. And here, lower the wavelength, lower the lambda naught. You see, again it is K max. These are the important formulas, and this one also. Here we see lower the lambda naught, lower is the work function, higher will be the energy. It is inverse proportionality. Higher will be the energy with which the electron is ejected from the metal. So this is the second part of the photoelectric effect. The third part is when we see an experimental diagram, an experimental proof, kind of an experimental diagram, from where we also gather a lot of information about the graphs which can be drawn on the photoelectric effect and what we derive from the graphs, which is very helpful for interpreting graphs also for the future purposes and chapters. Thank you.